Okay, thank you everyone for coming down this evening. Today we have Alexandre from Ahrefs here to tell you guys how to build a mini search engine from crawling to searching. So yeah, I'm going to let you take over.
Thank you. Hello, everyone. Thank you for coming in tonight. So, yeah, this meeting is being recorded. So we're gonna together we're gonna build like a mini search engine. But all the critical component of creating a search engine, we're gonna go over them in Python because it's easy to do stuff in Python. And I hope maybe some of these components can be useful to you for your hackathon project if you choose to use them. But overall, that's the goal. So I'm working from Ahrefs. So we are a company that specializes in SEO marketing analytics. And basically what we have is we have a crawler that goes over all the websites of the internet and download data on all the sites of the internet. At the time, this crawler is like the third most active crawler after Google and Bing. So we really have a lot of data. And we're using that data to make an in-house search engine, only relying on our data and not using any like Google or Bing data. And I'm working as a backend engineer for that project. So that's what I'm doing. And today I'm going to share a little about what I'm doing and my knowledge about search engines so that maybe you can apply it to your hackathon project. And I think it's interesting to know about how does Google work. So Ahrefs, the company is more about like SEO, so how to rank high on Google. But we really mastered the art of ranking high on Google, so now we want to make our own Google, basically. Yeah, and that's me. I like OCaml, if any of you is familiar with the language, and C++. Okay, so today we'll build a small-scale search engine. So the idea is to have all the building blocks that are important in a search engine and to make them in Python by hand. And there's three important steps to a search engine. The first one is crawling. So basically going from one website to another website and gathering information about all the websites that we care about and how they are connected within each other. The second is taking that raw data and making it easily searchable. So because it's nice to have the data, but if we don't have a way to search through it fast, we cannot do anything about it. Like you could check every page and every word of every page for the term you are looking for, but there are like smart ways to do that and very like pretty easy to do actually. So we'll go over that. And then there's the searching part, which is actually retrieving data about all the documents from your index and showing it to the user. Yeah. Yeah, so we'll use Python for everything. And we'll go over some pretty basic information retrieval techniques such as TF-IDF. Yeah, that's for next step. Yeah, I'm not really keen on slides, so this is just so you have an overview of what we're doing. But let's dig into the notebook. So have you all downloaded, like accesses the notebook link? So what you need to do in order to be able to run and edit it, please make a copy. So you have to do file and then save a copy in Drive and open that. And then you'll be able to execute the cells and make a modification if you want. Okay. So let's go. So I assume you're all familiar with Python and a notebook. So we'll have to install some requirements first. Nothing really crazy. The most important library, so we're starting with crawling. So the idea is we're gonna go over the internet from one website to the next and try to get information and to download the data about those websites. And for that, we need two libraries. The first one is a request to make HTTP queries. So we want to access this website like they will be accessed by a normal user. So we're going to be using the request Python library for that. And the second important library for crawling is called Beautiful Soup. And this is a library that takes HTML as input and allows us to parse that HTML and get out of this HTML only what we care about. So in our case, I think we'll only care about the title of pages and the content of the page and also the links that are in the page. So this should be done. It's a bit long, but okay. So this is some library we'll need to use. But the most important is, yes, Beautiful Soup and request for crawling. Right now you can see I put this delay. It's to avoid overloading the servers when crawling. It's very important when crawling. You don't want to be crawling too fast, otherwise you'll get banned from crawling. So actually, we can bump that to like 1 second to be safe. Like I don't know how much crawling from Google Colab is acceptable, but it worked yesterday. So the first thing to keep in mind when crawling is the robots.txt file. Who knows about the robots.txt file? Like raise your hand if you have heard that term. No. So this is basically on any website, this robots.txt informs the crawlers like Google, like Bing, and like the bot that we're doing, if you have the right or not to crawl the page, and which page you can crawl or not. It's very important when making a crawler to respect this robot.txt. And it's always, if this file is present, we have to take it into account. If it's not present, we don't really care. We can do whatever we want. And this robot.txt file was in the news recently because of AI. And people wanted to change how this file worked to incorporate AI. Like, can you train on my content or not? Because crawling for indexing purposes and crawling for AI purposes is a bit different. So how to get that file? This is like 3 basic Python function. So this one will just try to find the robot.txt file from the URL. Try to read it. And then we'll check if there's a file, it means we need to obey it. If there's no file, URL is allowed. So we can check for 3 files: NUS Hackers website, Google, and Wikipedia. So if I run this cell, this one, sorry. So I can see, for example, NUS Hackers doesn't have a robots.txt file. So I can crawl it because I'm not forbidden of doing anything. Google has one, and actually, if we show more line, like the first 20 line. Okay. So this is the robots.txt file of Google. And basically, it tells us you cannot crawl search. So it means we cannot make any Google search and crawl the output of Google that Google tells us. This is illegal, apparently. Like Google does not allow us to do that. And Wikipedia we can crawl, so that will be useful later because we're going to be crawling Wikipedia because the data on Wikipedia is very interesting for search engine. And yeah. So okay, let's crawl our first page then. So the processes for crawling a page is very straightforward. We first download the page using an HTTP request. Then once we have this page, we go through the content of that page and we get what we want out of it. So it's HTML. I assume you're familiar with how HTML looks like. Yeah, like that. This is HTML. And how do I go back? Okay, you cannot see it. This is horrible. Give me 1 second. I made a mistake. Okay. Yeah. Okay. So yeah, this is HTML. I'm sure you've seen it before. And basically, instead of having this raw file, which has a lot of field that we don't really care about, we only want to retrieve the title, the text that's actually in the file, and the links. The links will be very important for us. Yes, okay. So what we're doing is, yes, finding the title, okay? So first we get the page using the request library. Then we get the title. And then we remove JavaScript, we remove CSS. And then we get links. And we're gonna ignore for now, ignore completely actually links that are internal to the page. So links that are like that points to internal section of the page. And we're gonna ignore JavaScript and emails. Okay, so that's our crawling function. Nice. And now we can crawl the page. So let's start with the NUS Hackers homepage. Okay, so I ran that. When I ran that cell, it downloaded the page and it extracted the content of the page, so the title of the page. It told me it found 76 links. And that's the text content, the beginning of the text content of the page. So now you can try, put any website here. So I put National University of Singapore because I wanted to try a Wikipedia page. And depending on the page that you put, it would be longer. But in this case, it found National University of Singapore and Wikipedia. And we have a lot more links. So the thing with Wikipedia is everything is linked together. And a lot of links start in Wikipedia and end in Wikipedia. So it's nice to build a search engine that's like restricted to a small domain. Because when you start crawling, and you will see it very soon, you can start to go from one site to another site. So let's say to Facebook, and then you go to something else entirely. So you want to restrict the domain that you want to crawl usually, especially when your resources are limited. That's what we're going to make next. So because we have one page, but what we want is an automated robot that goes from page to page, crawls all the link of the page, and then uses that link to know which page it has to crawl next. And there's like two approaches we can make. So either we crawl one page, then we get the first link of that page and we crawl that page, and then we get the first link of that page and then we crawl that page. And this is a depth first approach. But the issue with that is we'll very, very, very quickly get out of the domain that we're crawling. And the domain in terms of internet domain, if we're starting with the NUS Hackers website, we'll get out of that website very quick. And if we want to crawl a subsection of the internet that is about a certain topic, like for example, programming, and we keep on taking the first link each time, we can end up somewhere else entirely. So it's not really the approach we want to do here. It's maybe useful in certain cases, but not for us. So instead, what we're going to do is use a breadth first approach, get a page, crawl all the links of that page, get all the link of the page, crawl all of the content, and then start from the first link of the page, do the same. Second list of the first page, do the same. Third link of the first page, do the same, and so on and so forth until we have done all the links. So this is what this function is doing. It's nothing really crazy. And for that, we'll be using a queue, like something that you have probably learned during a data structure and algorithm class. And we're going to say, OK, we want 5-page maximum. We still have our delay because we don't want to overload the website. And that's basically, yes, we're just getting all the links and continuing to crawl on all the links, as long as we still have pages to crawl. OK, so let's try that. And first, let's try on the NUS Hackers website. So each second, we're crawling a new page, getting a new link, getting a whole new set of links, and then continuing from the next link from the original page. So that's going to take like 20 seconds. And you can see all of the URL that we are crawling here. So that's all the website that we got. So it started here, and I assume from nushackers.org. It found the main page, and then it found the footer. And then it found interesting things like Google Map. So apparently there's a usage of Google Map on the page. And then some blog posts. It also tells us for the first page, we have 76 outbound links. So for that first page, there is 76 links that we could follow and crawl other parts of the web. So from one single seed page, we already have a lot of direction in which to crawl. And the main difficulty of crawling is knowing how to crawl the web, in which direction to go, what's the most efficient. But for us, we keep a simple approach. So we can compute the number of inbounding link for each page. So the number of links that point to that page. This is a statistic that is very useful for page ranking algorithm. So for example, the original Google algorithm, which is called a page rank, used a variant of that method. And we're going to make use of it later. So let's try this. Okay, so apparently out of all the pages that we have, and they all link to each other, we're going to see that very soon. The page that has the most links is this one, Hackers Call. So 19 out of the 20 pages that we have link to that page. And then apparently the blog posts have very little links because they're only linked on the front page. Okay, that's cool, but this is actually not telling us anything about how the NUS Hackers website is really connected. The nice thing about crawling is that you can display and show how the web is connected together, and it gives you a very good insight in things. And we can actually do that visualization ourselves here in Python. So using the networkx library, that is a library for graphs, because that's essentially what we have here is a graph. We have nodes that are websites, and we have edges that link websites to each other's. So we can build a graph out of that. So that's essentially what I'm doing here. I can run this. Yeah. And now to see the output, I have this crawl graph.html that I can download. You should also have it. And then I can open it. You see this. Perfect. Okay. So that's pretty cool because this is all of the website we crawled. And you can see this is the Hack&Roll 2025. This is this page. If I click on it, I have the URL. There's like 2 different Google Maps links, probably 2 different maps that are used somewhere. And then you have this whole set of pages which are mostly like the about page, archive, contact. So all of the header and footer that is present on all of the pages and that links to each other actually. So this is nice, but this is really a small scale. It's not, we cannot, and I don't know why it's spinning, but we cannot do much with that. What we would like to do is crawl a bigger, more interesting website than the NUS Hackers. So there's this game. I don't know if you've known about it. This Wikipedia game, and the idea is from one page in Wikipedia, find how to get to another page in the least number of links possible. And that's interesting because it means that you can get from one topic to any other topic on Wikipedia. So pages link a lot to each other. But at the same time, links in Wikipedia are very interesting because a page will link to pages of a similar topic. So you can kind of cluster pages based on topic or using this method. So what I did is this function is a Wikipedia crawler. It's essentially the same method as the one above, the same function. The difference is it only crawls Wikipedia. It starts by the start URL, and it only crawls Wikipedia/wiki URL. So I avoid going to any other website, and I try to stay to normal Wikipedia articles. So I avoid the resources, the templates, anything of that sort. So I ran that method, that function yesterday. And you can do it, but it will take 10 minutes. So maybe don't do it. I already have the data, and that's the second file I shared on Discord. It points to the data that you can download. And this data is wikiresult.pkl. So please download it and put it here. So drag and drop it here in files so that it's accessible to the script, to the notebook. But I will show you the content of running that cell once you have the file. So this is doing a couple of things. So first we crawl 1,000 Wikipedia pages, which is more than enough for our mini search engine demo. And here we have the domains that has been found. So we checked that we only have one domain. So we went through all of the pages and checked what the domain was. And we only have wikipedia.org, so it's good. And then this is the top pages by number of incoming links that we crawled. And so interestingly enough, the top pages are things like ISBN or DOI, or even the main page or Wayback Machine, because they are literally present on every page once or multiple times. I think Wikipedia sources oftentimes come from the Wayback Machine, so that's why it's present so many times. So okay, that's cool, that's cool. But what we want to see is the graph. We can make the same graph as we made before with some adjustment. So I will ignore. First, could you all get the file and drag and drop there and get this cell to run? Because yeah, it's good if you can follow, because this will be very important for the next part. So I'm going to run this. This is a very similar function that creates a visualization of our data. Okay, and this does a couple of things, but first I'm only going to concentrate on this. So it generates Wikipedia graph.html that I can also download. Okay, and that's our data. Okay, it's moving a bit because of the physics needed to create the graph, but let's wait a bit for it to stabilize. So it would be cool if you could reach that point so you can explore this graph a bit yourself. So the nice thing is we can see some interesting things. First, there's like some clusters that seems to be centered around one page. So for example, here. Now we found the North Pole apparently. So I think this is, can we see? Okay. Yeah, it's a bit buggy, but this is because a lot of Wikipedia pages include coordinates. So we ended up on coordinate system pages on Wikipedia, and then we have all of the meridians and that link to the North Pole and South Pole and longitude page, which makes sense. So okay, that's pretty obvious. What about this one? This one has to do with the Earth and also the parallel. So the nice thing about this graph is that themes or pages that are related on Wikipedia will be grouped together. If I go here, I can see another cluster. And actually, I didn't tell you with what I started this search. Uh, yeah, I started crawling with National University of Singapore. So we can assume the pages we're going to get to be related to this topic of university, because it will take all the links from that page and crawl them and so on and so forth. And when coming back here, we can see here a pretty big cluster here with NUS at the center. And then we have a lot of either names of people or names of other universities. And here you have countries and city linked to countries and more university. Yeah, we have a lot of university, but here you have even more general topics like World War II, even Marilyn Monroe. Yeah, we really went far here. And you can see on the outskirt of the graph, you have what's more unrelated to the next topic. So for example, Chief Justice of Singapore here is barely connected to the rest. So that's very, very cool data, I think. And this gives us an idea about the data we currently have after crawling. So now that we have our data, the next step is to use it to search. So is everyone okay? Did everyone manage to get the Wikipedia data? Okay, it's not very hard, but I just want to make sure. Oh, no. Okay, so I ran this cell before, and it does a couple different things. So it generates the visualization, and I have some statistics. So number of nodes. So I removed 2 pages, so I only have 1998 pages. Number of links is only 1,700, because for the purpose of the visualization, I removed almost all the links. Otherwise, it's impossible to visualize. Yeah, but the actual number of links is 20,000. One page usually has 100 links to other pages on the internet. So these statistics are not very accurate. But still, we can use this graph to determine what's the longest path between 2 different pages. So for example, if I want to go from Latin script to this university in Hong Kong, apparently it's 19 clicks. So I can assume that something like Latin script will be, I don't know actually, but very far away from university in Hong Kong, which are here. There's a couple of Hong Kong university. Yeah, but most of it is actually about university. So that's interesting. I could make a script that tells me, okay, given one page and one other page, how to get there the fastest. But that's not what we're here today. But you could make that. Okay. Okay, so that's it for part 1, the crawling part. Maybe let's take a 5 minutes break before I start the second part, because the second part will be more technical. So let's start at 42 maybe. Oh, thank you. Test. Okay. Okay, let's continue. So we finished the first part, which was getting the data, crawling, and now we want to search it. So this mini search engine can have a practical application. Basically, if you want, for example, to crawl the website of one user and proposing some very efficient search for that user, it will also be this kind of approach where you only crawl pages from their domain, for example. There's like some company doing some things like that. So the second part is we're going to index the pages. There's multiple steps in indexing the pages. So the first thing we're going to do is what we have is for each page, we have the title, where we have the links, and we have the content. We're going to take the content of the page, and we're going to go through all of the content of all pages and find all the words that are all on all the pages. And in order to find those words, we need to remove everything that's not a word, which is called tokenization. Tokenization is transforming one sentence into tokens that can be, in our case, it's words, but it can also be not words. Like, for example, in the case of AI, we also use tokenization for AI. So we're going to need some unit libraries, RE for regular expressions, and the rest is just to store our data. And also NLTK. So we have to run this cell. It will download this package, stop words. So that way we have access to all of the stop words in the English language, like and, to, or, and we can ignore them because they don't really bring a lot of information to us. So we don't want to index them. So that's the data we already have. Okay, so we want a function. This function will, from one piece of text, which is a string, a sentence, return a list of all the tokens, all of the words that are in that sentence. First, we want everything to be lowercase. Then we replace all punctuation with space. So all commas, all double colon with space. Then we split, and we remove the stop words. So we can test that function. So it removes all of these characters. Everything is now lowercase. So we have our tokenizer. And you can see that we also lost is, a, and, because we don't really care about it. It does not bring a lot of information for the purposes of search. And everything is lowercase. This tokenization process, we're right now applying it to the data, to the content of the pages, but we also are going to have to apply it to the input to our search query, because we will want our search query to be tokenized and all the terms of our queries to be lowercase in order to match them against our index. Okay, so the idea is to build a very, very basic index, the most basic index that we can have. This index will be an inverted index. And how it will work, it's a big dictionary, a big map that contains all of the words that are on all the pages of our index. So for all of the 1,000 pages, we go through all of the content and we check all of the words that are in the content. And we build this index with all the words here as key. And the value for each of these words will be a set of pages that contains this word. So for example, let's say for the word, like for the word here, Singapore, oh no. We'll have here National University of Singapore Wikipedia because it's on that page, and we'll have related pages like maybe the page about Singapore. For coding, we'll have pages related to coding, though there's not a lot in our dataset. So it's fairly simple to do that. So for all the pages that we crawled, we get all the text, so the title and the text. Then we tokenize it, so this will be a very big string that we tokenize. We remove the stop words. And then in our index, for that token, so for that token for that word, so in this case, Singapore, we'll add the URL. We add it to the list of URL that contains that word. And we return it as a dictionary. Okay, so we can run it. It will take a bit of time, but not so much. But this is usually the part that's very CPU intensive. For example, if you're running Microsoft Windows laptops, sometimes Windows is going to ask you, do you want to index a folder? And when indexing a folder, it's doing the same process of going through all of the files of the folder and building a more efficient representation of which file is where. Okay, it was not so long. So we have 200,000 unique words, which is quite a lot. And for example, for the word Python, apparently restriction of geographic data in China is valid for Python. But we also have Linux, like Cornell University, other university. For science, we have this. Okay, so it's a bit useful because now we can ask for a specific term, a specific token like Python, and we have all the websites that contain that word. But you can see it's not very accurate. Like when I'm searching Python, I don't really want to see something about China. Does not make sense. So we're not happy with this. I ran it again. Sorry. While that's running, what we can do in order to make our search more precise, usually when we search, we can search one term, but we can search also multiple terms if you want to search something more specific. And we can already do that very easily. We find pages that have all the terms. So how we do that is for all the terms of our query, we get all the set, and then we get at the end the intersection of the set. All the pages that are in the posting list, we call this a posting list for all of the terms that we are interested in. So that's what we're going to do here. Yeah, so first we tokenize our input. Then we get the first token. This first token not in index return set. If the first token is not in index, then we won't find any pages because we want all the pages that we return to have all of the tokens in their content. And then for each token, we add to the result the intersection of what's in the result and the posting list for that token. So this index of token is the list of all pages that have this token in their content. And we return those pages. Okay, got it straight. Okay. So we tried like 5 different queries here. So you can see that Querying Python compiler only returns Linux because we don't really have a lot of pages related to computer science in our dataset because we limited to 1,000 pages and we started in Singapore University. So we'll have a lot of universities or things related to Singapore. For example, here you can see. When I search Singapore, I have 464 pages. So half of my pages are related to Singapore, apparently. But if I search something like Merlion's statue, it gets better, actually. Like I get Singapore Tourism Board. So that's pretty cool because this is not a bad search result for Merlion. It's not the best, but you can assume that this page contains the word Merlion and will be a good search result. But this is not good enough because if we have only one term like Singapore, there's 500 pages. And if we query a word that's not in our index like this, unrelated word, 0 pages. So if you want, you can play a bit with it by changing those queries here and re-executing the cell. So for example, here, is NUS better? Yeah, NUS is a little better, you can see. Nanyang University, but University of Singapore is not near the top because there's no ordering. So maybe NTU is better than NUS actually. But we know it's not the case. So we want to add scoring. We want to know how good is actually this term for this query, for this page. Well, how good is this term for this page? So how good is NUS for NUS High School of Mathematics and Science? We know it's very good. But for Korea University Business School, not really. And how to do that? So that's where we get a bit more technical, or we're going to use the TF-IDF approach. And also the link-based ranking approach that I mentioned before to boost that. So we're going to use both approaches. We could also do synonyms and stemming. So for example, matching code to coding, so more like grammatical enhancement, but it's not needed for us for now. Okay, so that's the summary of what we've done with the basic indexing. So first, let's talk about TF-IDF. Yeah. Okay, this is just the same as before. Okay. So TF-IDF is term frequency inverse document frequency. So as I wrote here, it's a method to determine how important is a word to a document within a collection. So it's really about the relation between a specific word and a specific document. You compute this for a specific pair word document. So TF is the number of times that term appears in that document. And we divide it by the length of the document. And IDF is the inverse document frequency. So it measures how rare this term is across the whole corpus, the whole set of data. For example, talking about stop words, a word like the will be present. You can be sure that it will be present in all pages. So it's really not rare. So even if it appears a lot for a page, it appears a lot for the whole corpus as well. So its weight should not be very high. It should have a very, very low weight. And we compute that IDF by doing logarithm of the number of occurrence of the document. No, the size of the corpus, sorry, divided by the document frequency for that term. So the number of times that term occurs in the document. And then to get the TF-IDF, we multiply the TF of a term and a document with the IDF of a term. So That's the idea. So it seems pretty intuitive, actually. Like we want to set a very low weight for the document that for the terms that appear very frequently in all of the documents. But for the terms that are very rare, they will have a much higher weight. And this method of TF, IDF, and also derived method like BM25 are still used by state-of-the-art search software and are really considered one of the best things that we can do currently, even compared to more machine learning AI approaches, because it's statistical. And usually, modern search engine will use the two approaches together. So now we just have to compute it for all of our document and all of the terms. So this is where we have this function. Okay, so it's not very, very interesting, but we need to build this TF-IDF data. So we need first the document frequency. So that's a map. For each term, the number of documents that contain that term. And then for each URL, we want the document frequency for each URL, for each term that is in that document. So we can just compute them both. The first one is very easy because everything is already in the inverted index. It's just the length of the number of the data. And here we first get the text, then we tokenize it. Then we count the number of tokens that we have. And we add that to doc terms count for a given URL for a given token. And then to compute IDF, it's just log n divided by df. So we always compute IDF for a per term and for IDF, this is for a given term. So just for a given term in relation to the corpus of document. And we compute it with logarithm total documents divided by df. Okay. So we can try computing the IDF for some terms. So this will compute TF-IDF for every term that we have, all the 200,000 terms that we have. And then we'll test with some terms. So actually, I will create one cell here. So here for Singapore, for the term Singapore, our IDF is of 1.1. Okay. But what about a term that we think will be much more common or much more rare? Maybe much more rare. We know that we don't have a lot of document about coding, so maybe Python will be more rare, more common. Yeah, because if your IDF is higher, since it's the inverse, it means the term is more rare. And we want to give a higher weight to rare terms. And if I want a very, very common term, so the will not work, I guess, because it's not in the corpus, but maybe has. Also not in the corpus. Okay, about the Singapore, because I have a lot of documents about Singapore, actually. Oh, yeah. But you can play around this, try with different terms and see for that particular corpus that we have, for the particular data that we have, how common they are, how uncommon they are. Okay. So now we need to compute TF-IDF for documents. This IDF was for a given term, but TF-IDF is for document and term. And that's how we'll do it. So we need URL, queries, doc frequency, and we'll actually compute TF IDF during query time, because for TF IDF we need time frequency and IDF. We already computed IDF for all the terms and we saved it. So at query time, so when the user enters a query, we'll compute the term frequency for a term in a document and use it here. And we also keep the first approach of doing an AND search. So of getting all the document, of getting a document only if it has all of the terms. And then we sort by score. Okay, let's try again. Okay, I changed the queries because those were interesting. And now I get much more interesting results. Okay, if Python is still not the most interesting, but Linux comes first with a score of 37 or 35, and the next one is only 7. So it means that Linux is a lot more relevant for Python. And if I search Greek mathematician, I get a bunch of Greek mathematicians. So this seems to work. Liberal art college. That seems to be pretty okay. So now we already have good results. Same data, we just indexed it in a different way. We attributed scores, and it helped a lot. So now I'm going to showcase another method to determine how to rank page relative to each other. And this method is called link-based influence. It's one of the components of PageRank, because we also have information about how these pages link to each other. You remember the graph we had before told us how the pages were linking to each other, and we're not using that information at all. So we can try to add in this information into our TF-IDF computation. So yeah, this is by measuring the importance, the count of inbound links. PageRank works a little differently, but the idea is if a lot of pages are linking to you, it means you should be a good page. Actually, the idea in PageRank is if a lot of pages that have a lot of links are linking to you, then you're a good page. But we can stay at the normal degree. Like for example, yeah, if a lot of people are linking to one page, it means this is a page that should be considered. It works better for normal search because here it's Wikipedia, the data is already very clean. So we won't see a drastic improvement here, but it's still quite interesting to compute. So this is fairly simple. For each page that we have, we just check how many pages link to me. And that will be that value for that page, the number of inbound link for each page. So inbound counts. And then we can check what are the top pages. So of course, the first one will be National University of Singapore, because this is the page, I mean, it's not actually the first one, but this is the page I started with. So it makes sense that a lot of pages that National University of Singapore links to also link back to it. Also, the Wikipedia main page, all the pages link to, actually more than that, 2,000. So it means that there's 2 links to the main page per page. Then geographic coordinate system, it's not very interesting. But I could not show that with this graph. The problem is that you can imagine that if there is, like this here, if there is 2,000 or like 500 links to, oh no, like 200 links to a Malay language, for example, I don't know where it is exactly, it's somewhere here. I cannot load this graph. It's way too many links. So this gives us another way to think about how pages are related. And we could actually display a different graph by adding weights on the edges to be able to know how strong a link is or is not. And that will give us some insight into are some page heavily linked or not. Because here I'm only taking 1 or 2 links per page. Okay. So then let's try to combine this inbound link count with our TF-IDF approach. So we can combine them together using a alpha parameter that we multiply by the number of inbound link to that page. So very simple. I don't know why that won't load, but it's just TF-IDF score plus alpha times the number of links that that page has. Will be the score for that page for that term. So let's try it. Let's try to yeah, with a value of 0.01. And we can see that it also looks good. If we compare it, like Python, for example, looks better. Maybe. What did we have before for Python? Linux kernel, Cambridge. Okay, so Wayback Machine gets linked more, as a higher score as a result of all the links that point to it. But this is not maybe the best keyword for that. But maybe a more vague keyword will be will be better. Or like National University, like all of a lot of the pages that we crawled are university pages on Wikipedia, so hard to know in which order to put them. It's not easy. So maybe we want to change the alpha value. Maybe 0.01 is not optimal. So we can try with different alpha values. And I could try with a lot more value, but this time I just try with 4. And you can see that if alpha is too strong, it means we take too much into account the links. So we end up at a Wayback Machine all the time because Wayback Machine is linked by so many pages for the query USA. And if we don't take it into account, our top document changes too and gets maybe less specific. So actually, in this case, the best value is 0.01 because if we query USA, I think getting the Wikipedia page on the United States is what we're looking for. So let's use 0.01. So this is actually the end of this search engine workshop, but you can run this cell at the end, which the content is not really important. But if you run it, we should get a working demo of the search engine that we built. Okay, and I could. Yeah, nice. So this is my search engine demo. It uses everything that we've coded so far. There's nothing new except trying to get to put the description something relevant to our query. But we can query here, like if we query like NUS, for example. Okay, we get Yale NUS College, but this is pretty good. For the pages that we crawl, we get relevant pages for NUS. So I'm only showing the top 5 results, and I'm showing snippets of the content here. If you manage to run this, you can play a bit around with it. But that's about it for this introduction to search engines. Please tell me if you have any question or if something is not clear. Yeah. Yeah.
Are there any questions for speakers? About anything or any of the material? No? Okay, great. So, yeah, I'll just put up the.
Thank you.
So. Sure. Okay.
Oh yeah, I just want to mention, so we're actually at Ahrefs, we're actually building a real search engine, crawling all the internet. And if you want to try it, it's not yet production ready, so it's still a beta and still a bit slow, but if you want to try it, you can go to yep.com, and this actually should work well. Okay, this. Oh no. Okay, well, it doesn't work. This never happens, but you know. Anyway, you don't need that because you can build your own search engine now. So thank you for attending this workshop.
Okay, thank you all for coming down for the workshop as well. I will quickly just share a QR code where you can just drop off your feedback for the workshop.